Look up at the stars tonight, and you might feel small under that vast cosmic canvas. But what if I told you there's an invisible storm raging all around you, one that scientists still can't fully explain? Every second, trillions of cosmic particles streak through the air, piercing everything in their path, carrying whispers of the universe's deepest secrets. These aren't just random bursts of energy. Hidden within them are 27 bizarre patterns, anomalies so strange they've left even the brightest astrophysicists scratching their heads. Some of these patterns flicker like cosmic Morse code, while others form geometric shapes so precise they seem almost intentional. What are they trying to tell us? And why do they refuse to fit into any of our existing models of how the universe works? This isn't just about unexplained data or glitches in our telescopes. These cosmic riddles hint at something far bigger: gaps in our understanding so profound they could rewrite textbooks. Picture this: particles arriving with energies that defy the laws of physics, or signals that repeat at intervals too perfect to be random. Some theories suggest hidden dimensions or exotic new particles, while others whisper about phenomena we haven't even named yet. But here's what's truly thrilling. Every time we think we've cracked one mystery, another emerges, pulling us deeper into the cosmic unknown. So tonight, we're going on a journey, one that starts right here on Earth and stretches to the farthest edges of space. We'll unravel these 27 enigmas one by one, from the baffling cosmic voids where radiation simply vanishes to the eerie symmetrical pulses that some researchers believe could be signatures of something beyond our current science. By the time we're done, you won't just see the night sky differently, you'll feel it. Because the truth is, these aren't just puzzles for scientists in lab coats. They're clues waiting for all of us to piece together, hidden in plain sight, written in the language of the universe itself. Ready to decode them? Let's begin. Cosmic radiation isn't just background static from the universe. It's more like a high-energy fingerprint, left behind by some of the most violent events in existence. Imagine a supernova exploding millions of light years away, hurling particles across space at nearly the speed of light, or a black hole devouring a star, twisting the fabric of space-time so fiercely that it flings radiation in every direction. These cosmic cataclysms send waves of particles racing toward Earth, where they collide with our atmosphere in flashes of energy so faint only the most sensitive detectors can spot them. But here's where things get strange. While most cosmic radiation follows predictable patterns, like the steady hum of a distant engine, some signals stand out like a scream in the dark. Take the so-called cosmic rays with energies so absurdly high, they shouldn't exist under our current physics. According to Einstein's theory of relativity, particles traveling that fast should lose energy as they cross vast distances, yet these defy all expectations, arriving with a punch that leaves scientists reeling. Then there are the eerie symmetries, bursts of gamma rays that repeat at intervals so precise, they almost feel orchestrated. Some researchers argue these could be natural phenomena we just don't understand yet, while others wonder if we're glimpsing something far more extraordinary. The tools we use to study these mysteries are nothing short of miraculous. The Fermi Gamma Ray Space Telescope orbits Earth like a silent sentinel, capturing gamma rays with such precision it can trace them back to their origins. Ground-based observatories like the Pierre Auger Observatory in Argentina act like cosmic rain gauges, detecting particle showers as they slam into the atmosphere. But even with this arsenal of technology, some signals refuse to make sense. Why do certain high-energy particles arrive in clusters, as if they're being funneled from a single point? And what explains the baffling cold spots in cosmic radiation regions where the expected background noise simply drops off? One leading theory suggests these anomalies could be echoes of hidden dimensions, wrinkles in space-time we can't yet perceive. Another proposes ultra-rare particles, born in conditions so extreme they rewrite the rules of quantum mechanics. And yes, a handful of scientists entertain even wilder possibilities, like advanced civilizations manipulating energy on scales we can't fathom. But the truth is, every answer we find only leads to more questions, because cosmic radiation isn't just a puzzle to solve, it's a mirror reflecting back how much we still don't know about the universe. And that's what makes this search so exhilarating. Every anomaly, every glitch in the data is a chance to discover something that could change everything. Deep in the heart of our galaxy, something impossible is happening. The Milky Way's core should be a predictable sea of radiation, a chaotic but measurable mix of energy from stars, black holes, and interstellar gas. Yet when scientists pointed telescopes toward this region, they found something that defies all expectations, an eerie excess of gamma rays glowing like a ghostly halo around the galactic center. These aren't just random bursts, they form a near-perfect symmetrical pattern, as if some unseen hand arranged them deliberately. Current astrophysics can't fully explain this galactic center anomaly. One leading theory points to dark matter, the mysterious, invisible substance that makes up most of the universe's mass. If dark matter particles collide and annihilate each other, they could release gamma rays in exactly the pattern we're seeing. It's a tantalizing idea because this could be our first direct clue to understanding what dark matter actually is. But there's a catch: the signal is almost too clean, too precise. Natural cosmic events rarely produce such uniformity. That's why other researchers argue the anomaly might come from something entirely different, a dense cluster of pulsars, the spinning corpses of dead stars, emitting gamma rays like cosmic lighthouses. The trouble is, we haven't found nearly enough pulsars in that region to account for the signal, unless, of course, there's a hidden population of these objects, lurking just beyond our detection. Then there's the strangest possibility of all. The pattern's symmetry is so exact, it raises an unsettling question. Could this be evidence of something even more exotic, like a previously unknown force or a flaw in our understanding of space-time itself? Some theorists speculate about topological defects, ancient wrinkles in the fabric of the universe, left over from the Big Bang, releasing energy in ways we've never seen before. What makes this mystery so thrilling is that it's not just about one anomaly, it's a doorway. If the answer lies in dark matter, it could unlock secrets about the universe's hidden structure. If it's pulsars, we'll have to rethink how stars live and die. And if it's something entirely new, well, that's when the real fun begins. Because every time we peel back one layer of the cosmos, we find another waiting beneath, more intricate, more baffling, and more beautiful than we ever imagined. Now let's zoom in on one of the most perplexing cosmic mysteries, the hotspots. Imagine throwing a handful of sand into the wind and watching it scatter randomly, except a few grains inexplicably land in perfect little piles, defying the chaos around them. That's what cosmic ray hotspots look like to scientists. These aren't just slightly denser patches of radiation. They're blazing anomalies, regions of space where cosmic rays arrive with such intense focus. It's as if some invisible force is funneling them there. The strangest part, these hotspots don't match up with any known cosmic landmarks. Supernova remnants, active galaxies, even the violent jets of black holes, none of them line up with these clusters. It's like finding footprints in the snow with no sign of who or what left them. One of the most famous examples sits in the constellation Ursa Major, where detectors have picked up a persistent knot of ultra-high-energy particles. These aren't your average cosmic rays. They pack enough punch to rival a well-thrown baseball, except they've traveled billions of light years to get here. So how do particles with that much energy stay so tightly grouped? According to our current understanding, cosmic rays should scatter as they travel, their paths twisted by interstellar magnetic fields like leaves in a storm. Yet these hotspots remain stubbornly coherent, as if something is correcting their course mid-flight. Some theorists suggest the answer lies beyond our galaxy, perhaps in the vast voids between galactic clusters, where mysterious phenomena could be accelerating particles to unimaginable speeds. Others wonder if we're seeing the fingerprints of cosmic strings, hypothetical defects in space-time left over from the Big Bang, warping the paths of these particles like invisible highways. Then there's the energy problem. The highest energy cosmic rays in these hotspots carry millions of times more power than anything we can produce in particle colliders. If they're coming from distant galaxies, they should have lost most of their energy along the way due to interactions with the cosmic microwave background, the faint afterglow of the universe's birth. The fact that they haven't suggests two mind-bending possibilities. Either these particles didn't travel as far as we think, hopping across space via some short-cut we don't yet understand, or they're being continuously re-energized by something along their path. What's truly fascinating is how this mystery ties into others. Some of these hotspots coincide with cold spots in the cosmic microwave background, regions of the sky that are slightly cooler than they should be. Could these be the cosmic equivalents of shadows, cast by structures or forces we can't yet see? Or perhaps they're signposts pointing toward something even more profound, like flaws in our understanding of gravity itself. Every time we think we're closing in on an answer, the universe throws another curveball, reminding us that the cosmos still holds cards it hasn't shown us yet. And that's what makes these hotspots so thrilling. They're not just anomalies. They're invitations to look deeper, to question harder, and to wonder what else might be out there, waiting to be discovered. Among the sea of data collected by X-ray telescopes, there's a whisper, a faint but stubborn spike at 3.5 kiloelectron volts that refuses to fade into the background. This isn't just noise, it's a signal that's been spotted again and again, flickering like a distant beacon across multiple galaxies, from the Perseus cluster to the Andromeda galaxy. At first glance, it might seem insignificant, a blip in the data, a quirk of instrumentation. But when the same exact spike appears in entirely different corners of the universe, scientists start to ask, what if this is the universe trying to tell us something? The most tantalizing explanation, dark matter, the elusive substance that makes up 85% of the universe's mass, might finally be revealing itself. According to one theory, certain types of dark matter particles could decay over time, releasing X-rays at precisely 3.5 kiloelectron volts. If true, this would be one of the most monumental discoveries in modern physics, giving us our first direct glimpse into the invisible scaffolding of the cosmos. But there's a problem. The signal is everywhere. It's not just coming from regions dense with dark matter. It's also appearing in places where dark matter should be sparse, like the centers of galaxies where ordinary matter dominates. This inconsistency has left researchers divided, with some calling it a smoking gun for dark matter, while others dismiss it as an artifact, a glitch in how our instruments process X-ray light. Then there's the instrumentation camp. Certain elements like sulfur and potassium can emit X-rays at similar energies under specific conditions. Could the spike simply be the collective glow of these atoms, heated to extreme temperatures in the hearts of galaxies? It's possible, but the signal's uniformity across such diverse environments makes this explanation feel shaky. If it were just background noise or instrumental effects, why does it persist so consistently, like a cosmic metronome ticking in perfect sync across the universe? The debate has sparked a race to solve the puzzle, with teams reanalyzing old data and designing new experiments to isolate the signal. One proposed mission, the X-ray Imaging and Spectroscopy mission, aims to study the 3.5 kiloelectron volt spike with unprecedented precision, potentially settling the argument once and for all. But until then, the mystery lingers, a reminder that even the quietest signals can hold the loudest implications. Whether it's dark matter whispering its secrets or something entirely unexpected, this tiny spike in the data represents something far bigger, a crack in our understanding waiting to be widened. And that's the beauty of cosmic mysteries. They don't just challenge what we know, they challenge how we think, pushing us to look deeper, question harder, and wonder what else might be hiding in the shadows of the data. Rising from the heart of the Milky Way like twin titans, the Fermi Bubbles stretch 50,000 light-years into space, a pair of colossal gamma-ray structures so vast they dwarf our entire galaxy. These cosmic megastructures glow with the aftermath of unimaginable energy, their origins shrouded in mystery. But here's what truly baffles scientists: their edges aren't fuzzy or diffuse like most galactic phenomena. Instead, they're razor-sharp, as if sliced by a cosmic scalpel. Picture blowing smoke into the air. It disperses, softens, blends into the surroundings. That's how energy typically behaves in space, but the Fermi Bubbles defy this logic. Their boundaries are so crisp they cast shadows in the gamma-ray sky, blocking other radiation like a physical barrier. Computer simulations can't replicate this precision, not even when modeling the most violent galactic events, like the supermassive black hole at our galaxy's core erupting in a cataclysmic outburst millions of years ago. So what could carve such clean edges? One theory points to dark matter, the universe's invisible scaffolding. If dark matter particles interact in just the right way, they might create shock waves that sculpt these sharp borders. Others propose magnetic fields of unimaginable strength, acting like cosmic cookie cutters on the bubble's glowing gas. But there's a wilder possibility. What if the bubbles aren't remnants of an ancient explosion at all, but ongoing structures fed by some hidden engine deep in the galactic core? The timing adds another layer of intrigue. The bubble's gamma rays suggest they formed relatively recently, perhaps a few million years ago. That's a blink in cosmic terms, raising questions about what dramatic event could have left such a fresh, unmistakable mark. Some researchers speculate it might link to the mysterious Gaia sausage, a ghostly cluster of stars orbiting the Milky Way, the remnants of a smaller galaxy torn apart by our own. Could that collision have triggered the bubble's formation? Then there's the energy problem. The gamma rays pouring from the bubbles require a source far more powerful than anything we've observed in the modern Milky Way. If our galaxy's black hole is quiet now, what could have awakened it to such fury in the past? Or more tantalizingly, is there another force at work, something we haven't yet imagined? Every answer leads to deeper questions, but that's what makes these bubbles so extraordinary. They're not just relics, they're a cosmic crime scene, and the clues we're gathering could rewrite the story of our galaxy's most violent chapters. What's clear is this: the Fermi Bubbles aren't just another space oddity. They're a challenge, a reminder that even in our own galactic backyard, the universe still holds secrets so profound, they force us to rethink everything we thought we knew. And as we peel back the layers, one revelation at a time, we're not just uncovering the past, we're glimpsing the hidden forces that shape galaxies and perhaps the destiny of our own. Somewhere in the depths of space, there's a place where the universe feels empty, not just quiet, not just dark, but unnervingly void of the cosmic radiation that fills every other corner of the cosmos. Astronomers call it the Great Cosmic Void, a region spanning hundreds of millions of light years where the usual hum of background radiation drops to near silence. It's as if someone turned off the universe's soundtrack in this one spot, leaving behind a silence so profound it sends chills down the spines of researchers. What makes this void so baffling isn't just its size, it's the sheer impossibility of its existence. According to everything we know about cosmology, space should be roughly uniform on large scales, like a cosmic tapestry woven with consistent threads of energy. Yet here, the fabric frays into nothingness. Imagine walking through a dense forest where every inch teems with life, only to stumble into a clearing where not even a single blade of grass grows. That's the scale of this anomaly. Theories swirl around this cosmic desert like stardust. One possibility is that something colossal, something we can't yet detect, swept through this region, absorbing or scattering radiation like a celestial sponge. Some models suggest the void could be the aftermath of a collision between universes in the multiverse, a scar left behind when two realities briefly brushed against each other. Others propose it's a flaw in the very structure of space-time, a place where the rules of physics twist just enough to silence the cosmic noise, but the most mind-bending hypothesis. This void might be a window into another dimension. If extra dimensions exist curled up so tightly we've never detected them, they could occasionally leak into our own, warping space in ways that siphon away energy. Picture a balloon pressed against a wire fence. Where the fence touches the balloon, tiny gaps form. In this case, the fence is our universe and the balloon is something else entirely. What's equally puzzling is how this void contradicts one of astronomy's bedrock principles, the cosmological principle, which states that the universe should look roughly the same in all directions on large scales. The Great Cosmic Void isn't just a minor deviation, it's a screaming outlier forcing scientists to ask, is our principle flawed, or is this void the exception that proves the rule? Efforts to study it further are fraught with challenges. Traditional telescopes struggle to observe nothingness. You can't point a lens at empty space and expect answers. Instead, researchers rely on subtle distortions in the cosmic microwave background, the faint afterglow of the Big Bang, to map the void's edges. Even then, the data raises more questions than answers. Why does the void's boundary appear sharper than it should? And why do some particles, like neutrinos, seem to pass through it unaffected, while others vanish entirely? This isn't just a curiosity for theorists. If the void's existence hints at new physics or even a multiverse, it could redefine our understanding of reality. Every time we think we've grasped the universe's rules, anomalies like this remind us how much lies beyond the edges of our maps. The Great Cosmic Void isn't just a blank spot in the sky. It's a question mark written in the language of the cosmos, daring us to look deeper into the dark. Deep in the cosmic radiation data, there's a moment where the rules seem to bend, literally. Scientists call it the knee, not because the universe has joints, but because the graph of cosmic ray energies takes a sharp turn, like a runner suddenly changing direction. At around 1 quadrillion electron volts, the number of high-energy particles drops off dramatically, as if some invisible barrier is preventing them from going further. This isn't just a statistical quirk, it's a cosmic roadblock, and no one knows exactly why it's there. Think of it like driving a car faster and faster until, without warning, the engine simply refuses to push beyond a certain speed. For cosmic rays, that limit appears to be hard-coded into the fabric of reality. One explanation points to our galaxy's magnetic fields. Perhaps they act like a cosmic sieve, filtering out the highest energy particles over vast distances. But here's the catch. Some particles do break through, arriving with energies far beyond the knee, which suggests the truth might be stranger. That's where exotic physics enters the picture. Some theorists argue the knee could mark the edge of our current understanding, a sign that particles are bumping into the granular nature of space-time itself. Imagine space as a frothy sea at the smallest scales, with tiny bubbles of quantum foam creating friction for ultra-high-energy particles. It's a radical idea, but if true, it would mean the knee isn't just a curiosity. It's a glimpse into the quantum structure of the universe. There's another, even wilder possibility. The knee might be evidence of particles from beyond our galaxy slamming into a universal speed limit. Just as nothing can outpace light, perhaps there's another ceiling we haven't discovered yet, one that kicks in at energies so high they're barely comprehensible. If that's the case, the knee isn't a barrier. It's a signpost pointing toward physics we've yet to imagine. What makes this mystery so compelling is its universality. No matter where we look in the Milky Way, the knee appears at the same energy threshold, like a cosmic drumbeat echoing across the galaxy. That consistency hints at something fundamental, a rule woven into the fabric of existence itself. Whether it's space-time foam, galactic magnetic fields, or something entirely unseen, one thing is clear. The universe is hiding its secrets in plain sight, written in the language of bending graphs and elusive knees. And every time we think we're close to an answer, the cosmos reminds us there's always another layer to unravel. Earth spins like a silent metronome, marking time with perfect regularity, but something in the cosmos might be keeping pace. Deep in the data from cosmic ray observatories, scientists have spotted a pulse that defies explanation, a 12-hour cycle perfectly synchronized with our planet's rotation. It's as if the universe is tapping its foot to Earth's rhythm, and no one knows why. Here's what makes this so bizarre. Cosmic rays are supposed to be isotropic, meaning they should arrive evenly from all directions, like rain falling uniformly on a windshield. But these detectors are catching something different, a faint but consistent ebb and flow, cresting every 12 hours like cosmic tides. At first, researchers assumed it was an artifact, a glitch caused by Earth's magnetic field bending incoming particles. But the math doesn't add up. Our planet's magnetism shouldn't create such a precise, repeating signal. It's like hearing a heartbeat in static, a pattern too clean to dismiss as noise. One theory points to an unseen structure in our galaxy's magnetic field, a vast invisible current that interacts with Earth's rotation to create this rhythmic pulse. Picture the Milky Way as a colossal machine with magnetic gears turning in sync with our planet's spin. But there's a problem. We've mapped galactic magnetism extensively, and nothing in our models predicts this 12-hour whisper. Then there's the far more provocative idea that something out there is actively tuning this signal. Could an exotic astrophysical object, like a rapidly spinning neutron star or a distant black hole binary, be emitting cosmic rays in a beam that sweeps past Earth like a lighthouse? It's not impossible, but the precision is unnerving. For a beam to align so perfectly with our rotation, it would need to be impossibly fine-tuned or intentionally aligned. The implications ripple outward. If this cycle isn't a fluke, it challenges one of astronomy's core assumptions, that the universe is fundamentally isotropic. What if, on some scale we've yet to perceive, the cosmos has a hidden structure, a grid, a rhythm, an architecture we're only glimpsing in fragments? Or worse, what if we're seeing the shadow of something even stranger, like a flaw in space-time itself? For now, the 12-hour cycle remains a quiet enigma, ticking away in the background of more obvious cosmic mysteries. But its persistence is a reminder. Sometimes the universe's loudest messages come in the softest whispers. And the more we listen, the more we realize how much we've yet to hear. Somewhere in the void between stars, the universe is breaking its own rules, quietly manufacturing more antimatter than it should. Specifically, positrons, the antimatter twins of electrons, are streaming through space in numbers that defy every prediction. You'd expect these particles to be rare, fleeting things, annihilating instantly when they meet their matter counterparts. Yet detectors on Earth and in orbit keep catching them in abundance, like uninvited guests at a cosmic party that wasn't supposed to include them. The most obvious suspects are pulsars spinning stellar corpses that whip particles to extreme energies, potentially creating positrons as a byproduct. But here's the catch. Even if you add up every known pulsar in the galaxy, their combined output falls woefully short of explaining the surplus. It's like trying to fill an ocean with a garden hose. This leaves scientists staring at two possibilities, each more intriguing than the last. Either we're missing something fundamental about how pulsars work, or something far stranger is at play. That's where dark matter enters the stage. Certain theoretical dark matter particles, when they collide, could annihilate each other in bursts of energy, producing positrons as a signature. Imagine two invisible ghosts crashing together and leaving behind glowing footprints. If this is true, the antimatter surplus isn't just a curiosity. It's our first tangible clue to decoding dark matter's nature. But skeptics point out a problem. The positron excess doesn't quite match the energy spectrum these collisions should produce. It's close but not perfect, like finding a key that almost fits a lock. Which raises the wildcard option, an undiscovered astrophysical factory churning out antimatter on an industrial scale. Picture a celestial forge hidden in some distant corner of the galaxy, where extreme conditions rip particles apart and stitch them back together as their antimatter opposites. Some theorists speculate about primordial black holes, tiny, ancient relics from the Big Bang, vaporizing in bursts of radiation that favor antimatter. Others wonder if we're seeing the handiwork of exotic stellar objects like quark stars, where matter itself breaks down into more fundamental components. The implications ripple far beyond astrophysics. If antimatter is more abundant than we thought, it challenges one of cosmology's bedrock assumptions: why our universe is dominated by matter at all. According to the Big Bang, matter and antimatter should have been created in equal amounts, leaving nothing but energy as they annihilated each other. The fact that we exist means something tipped the scales. This surplus could be a hint, a faint echo of that primordial imbalance. For now, the mystery lingers, suspended between discovery and understanding. Every new positron detected is a breadcrumb leading us deeper into the cosmic unknown. Whether the answer lies in dark matter, unseen astrophysical engines, or something beyond our current theories, one thing is certain: the universe is keeping secrets, and they're written in the language of antimatter. And each time we think we're close to deciphering them, the cosmos reminds us some codes take more than a lifetime to crack. Light from quasars, those blazing cores of ancient galaxies, should scatter randomly across the sky, their polarizations as chaotic as confetti in a storm. Yet when scientists analyzed light from over 100 quasars separated by billions of light years, they found something that sent shockwaves through cosmology. Their polarizations weren't random at all. Instead, they aligned along a single, invisible axis, as if the universe itself had drawn a line in the cosmic sand and whispered, "This way." This eerie alignment, dubbed the axis of evil by researchers, shouldn't exist. According to the cosmological principle, The universe must look roughly the same in all directions on large scales, no preferred directions, no hidden grids. But the quasars seem to defy this rule, their light vibrating in sync across unimaginable distances. Some theorists argue this could be a fossil imprint from the birth of the cosmos, a relic of the primordial magnetic fields that shaped the universe in its first moments. Imagine the Big Bang not as a perfect explosion, but as a spinning top, leaving behind a faint directional preference etched into spacetime itself. Others propose an even more radical idea. These alignments might trace the skeleton of a cosmic superstructure, a web of dark matter or unknown energy stretching across the observable universe. Picture a spider's silk threading through the cosmos, tugging on light as it passes. If true, this would mean the universe isn't just lumpy with galaxies and voids, it's threaded with invisible architecture, guiding light like rails on a cosmic railroad. Then there's the unsettling alternative. What if the alignment isn't physical at all, but a flaw in our understanding of polarization itself? Could quantum entanglement, operating across galactic distances, be locking these light waves into sync? Or is there some overlooked property of interstellar dust, bending quasar light in ways we haven't accounted for? The problem is, no tweak to existing physics cleanly explains the scale of this phenomenon. The implications are staggering. If the axis is real, it challenges not just the cosmological principle, but the very foundations of how we model the universe. Our entire understanding of cosmic expansion, galaxy formation, and even dark energy relies on the assumption of uniformity. A preferred direction would force us to rewrite textbooks or consider that we're seeing the shadow of something far larger, a structure so vast it makes our observable universe seem like a single stitch in an infinite tapestry. For now, the aligned quasars remain one of cosmology's most persistent puzzles, a whisper of order in what should be chaos. Whether it's a relic of creation, a sign of hidden dimensions, or a cosmic illusion, one thing is clear: the universe is still teaching us how little we truly know. And sometimes the most profound lessons come not from the answers we find, but from the mysteries that refuse to be solved. In the grand cosmic recipe that forged the elements, everything seemed to add up: hydrogen and helium in abundance, trace amounts of heavier metals, all matching predictions from the Big Bang's nuclear cauldron. But there's one ingredient that refuses to follow the math: lithium. According to our best models, the early universe should have produced about 3 times more lithium than we actually observe. It's as if someone snipped a section from the periodic table, leaving behind a gap that defies explanation. This isn't just a minor accounting error. Lithium is one of the 3 lightest elements forged in the Big Bang's aftermath, alongside hydrogen and helium. Its expected abundance is etched into the bedrock of cosmology, a prediction so fundamental that finding it off by even a small margin would raise eyebrows. But the discrepancy isn't small. It's a cosmic-scale shortage, with stars and interstellar gas showing lithium levels so low, it's like the universe misplaced an entire stellar warehouse of the stuff. So where did it go? One camp of theorists argues that our understanding of nuclear physics might be incomplete. The reactions that produced lithium in the early universe could have been far more complex than we've modeled, with unknown pathways allowing lithium to break down or transform into other elements. Picture a factory assembly line where some of the product mysteriously vanishes before reaching the warehouse. Only in this case, the factory is the entire cosmos, and the assembly line ran for just minutes after the Big Bang. Others propose a more dramatic solution. Lithium might have been locked away in places we can't easily observe. Imagine ancient stars acting like cosmic sponges, absorbing primordial lithium and burying it deep in their cores where it's shielded from detection. Some red giants, for instance, show lithium in their outer layers that shouldn't exist unless it's being dredged up from hidden reservoirs below. But even if every star in the universe were hoarding lithium, the numbers still don't quite add up. Then there's the wildcard possibility something beyond standard physics is at play. Could exotic particles or undiscovered forces have scavenged lithium in the universe's infancy? Certain dark matter candidates, for example, might interact with ordinary matter in ways that preferentially destroy lithium, leaving behind the deficit we see today. Or perhaps the early universe wasn't as uniform as we think, with pockets of space where lithium production was mysteriously suppressed. What makes this mystery so frustrating and so thrilling is that it's not just about lithium. It's a stress test for our entire understanding of nucleosynthesis, the process that built the elements. If we've misread lithium's role, what else might we have gotten wrong? Every unexplained atom is a clue, a whisper from the universe's first moments, hinting that the story we've told ourselves might need rewriting. And until we solve it, this missing lithium remains a quiet challenge, a cosmic check your work note scribbled in the margins of the Big Bang's blueprint. The universe is supposed to expand evenly in all directions, like a balloon inflating. So why are thousands of galaxy clusters all drifting the same way, like leaves caught in a hidden current? Astronomers call this the dark flow, and it's one of the most unsettling cosmic mysteries of our time. Imagine dropping hundreds of paper boats into a river, expecting them to scatter randomly, only to watch them all glide steadily downstream, pulled by some unseen force. That's precisely what's happening on a galactic scale, with entire clusters of galaxies moving toward a single patch of space at speeds exceeding 2 million miles per hour. This isn't just a slight statistical tilt. The dark flow spans billions of light years, involving clusters so distant their motion should be dominated by the universe's expansion, not some mysterious tug. Yet there they go, defying expectations as if something colossal, something beyond the edges of our observable universe, is exerting gravity on them, the leading theory. These clusters might be feeling the pull of an enormous structure lurking in the unobservable cosmos, perhaps a supermassive concentration of matter left over from the Big Bang's uneven infancy. Picture a mountain so vast, its shadow falls across the horizon we can't even see. But there's a wilder possibility. The dark flow could be evidence of a neighboring universe brushing against our own. In multiverse theories, other universes might exist like bubbles in a frothy sea, occasionally nudging one another. If one of these bubbles grazed ours, its gravitational influence might explain the strange, coordinated motion we're witnessing. It's a staggering idea, proof that our cosmos isn't alone, written in the silent drift of galaxies. Skeptics argue it could all be an illusion, a trick of incomplete data or measurement errors. After all, tracking the motion of galaxy clusters across such vast distances is like trying to measure the speed of a crawling ant from orbit. But the signal persists, surviving repeated scrutiny and even showing up in independent studies. If it's real, the implications rewrite our understanding of reality. The cosmological principle, the idea that the universe is uniform on large scales, would shatter, replaced by a cosmos lopsided with unseen forces. What's most haunting is the scale. The dark flow's pull seems to originate from a direction eerily aligned with other cosmic anomalies, like the infamous axis of evil in the cosmic microwave background. Could these be connected, pieces of some deeper puzzle we've only begun to glimpse? For now, the dark flow remains a ghostly fingerprint on the cosmos, a hint that the universe's greatest secrets might lie not in what we see, but in what we can't. And every galaxy caught in this current is a silent witness, drifting toward answers we're not yet equipped to understand. gamma-ray circles glow in the night sky like cosmic smoke rings, perfectly round, eerily symmetrical, and utterly baffling. These aren't the messy aftermath of supernova or the scattered debris of colliding stars. They're pristine loops of high-energy light, some stretching hundreds of light-years across, with no visible source at their centers. It's as if someone dipped a celestial paintbrush in pure gamma radiation and drew flawless circles across the cosmos, leaving scientists to wonder, what kind of cosmic event leaves behind a signature this clean? At first glance, they resemble the echoes of ancient explosions, shockwaves from long-dead stars perhaps, rippling outward and lighting up interstellar gas. But there's a problem. When stars explode, they leave behind chaotic, uneven remnants like the Crab Nebula's tangled filaments. These circles, by contrast, are geometric perfection. Their symmetry is so precise, it rules out nearly all known astrophysical processes. Even more puzzling, some of these rings appear to float in isolation, untethered to any known galaxy or stellar nursery. That's where cosmic strings enter the conversation, hypothetical defects in spacetime, thinner than an atom but denser than a neutron star, left over from the universe's fiery birth. Theory suggests these strings could vibrate like guitar strings, releasing bursts of energy as they snap or decay. If one were to collapse, it might release a spherical shockwave that would appear from our vantage point as a perfect circle. It's an elegant idea, but there's a catch. We've never directly detected cosmic strings. If these rings are their handiwork, it would be the first tangible evidence that these spacetime flaws actually exist. Then there's the timing mystery. Some circles seem impossibly old, their light traveling for billions of years before reaching us, while others appear surprisingly fresh. If they're all caused by the same phenomenon, why do they span such a vast range of ages? One radical proposal suggests they're not remnants of one-time events, but recurring phenomena like cosmic geysers, periodically erupting in gamma rays. Picture a dormant engine buried in the fabric of space, flaring to life at intervals we can't yet predict. The most tantalizing clue lies in what's missing. These circles glow in gamma rays but leave no trace in other wavelengths, no X-rays, no visible light, no radio whispers. It's as if whatever created them operated in a hidden language, speaking only in high-energy photons. This spectral silence deepens the enigma, ruling out ordinary stellar processes and pointing toward something far more exotic. Could they be the aftermath of collisions between invisible particles, or the signatures of dark matter annihilations? What's certain is this: these circles aren't just celestial oddities. They're cosmic road signs pointing toward gaps in our understanding so vast, they might as well be portals. Every time we think we've mapped the universe's extremes, phenomena like these remind us the cosmos has a habit of drawing outside the lines, and until we decipher their origin, these ghostly rings will keep hovering in the data, silent, perfect, and utterly unresolved. On the cosmic microwave background, the afterglow of the Big Bang itself, there's a patch of sky that doesn't belong, dubbed the cold spot. This region is colder than it should be by a margin so significant, it's like finding a snowball in the middle of a desert. At first glance, it might seem like a minor statistical fluke, but the numbers don't lie. The odds of such a chill appearing randomly are less than 1 in 50. This isn't just a curiosity, it's a full-blown crisis for cosmology, because our best theories can't fully explain why it's there. The leading explanation points to a supervoid, an enormous, mostly empty region of space where matter is so sparse, light passing through loses energy, creating a cooling effect. Picture walking through a pitch-black forest and stumbling into a clearing where the trees vanish for millions of light years. But here's the catch. When astronomers searched the cold spot's location, they found no void large enough to account for the temperature drop. The ones we've spotted are like puddles trying to explain an ocean. That's where things get truly strange. Some theorists argue the cold spot might be a bruise, a relic from a collision with another universe in the multiverse. According to this idea, our cosmos might have bumped into a neighboring bubble universe in its infancy, leaving behind a gravitational imprint that cooled this patch of sky. It's a radical notion, but the math holds a haunting allure. The cold spot's size and temperature profile align eerily well with what such a collision might look like. Yet skeptics aren't convinced. If another universe grazed ours, why is there only one cold spot? Shouldn't the sky be littered with them? Others propose the spot could be a shadow cast by something even more exotic, a cosmic texture, a defect in spacetime's fabric left over from the universe's violent birth. These hypothetical structures would warp space around them, subtly distorting the background radiation in ways that mimic cooling, the most unsettling possibility. The cold spot might not be an anomaly at all, but a warning. What if it's revealing a flaw in inflation theory, the cornerstone of modern cosmology? Inflation posits that the early universe expanded uniformly, seeding the evenness we see in the cosmic microwave background. But the cold spot's stark deviation hints that the universe's infancy might have been messier, more uneven than we've assumed. For now, the cold spot remains a tantalizing enigma, a cosmic Rorschach test inviting scientists and the rest of us to peer deeper. Whether it's a fingerprint from another reality, a whisper from spacetime's birth pangs, or a crack in our foundational theories, one thing is certain: the universe is still writing its own rules. And sometimes the coldest corners hold the hottest secrets. Most cosmic explosions flare once and vanish, but deep in the static of space, a few defy the rules, blinking on and off like malfunctioning cosmic traffic lights. Fast radio bursts, those mysterious millisecond flashes of radio energy, usually strike without warning and never return. Yet a handful of them repeat, firing off bursts at intervals so irregular they seem almost deliberate. What makes these repeating FRBs so baffling isn't just their persistence, it's the way they pulse. Unlike the predictable spin of a neutron star or the steady tick of a pulsar, these bursts erupt in chaotic clusters, sometimes falling silent for months before suddenly unleashing a flurry of signals. Even stranger, a few exhibit eerie time symmetries, with bursts spaced at intervals that mirror mathematical sequences too precise to dismiss as coincidence. It's as if whatever's producing them is following a script written in a language we don't yet understand. The leading suspect, magnetars neutron stars with magnetic fields so intense they could strip the data from a credit card halfway across the galaxy. When these stellar corpses undergo starquakes or magnetic upheavals, they might unleash the titanic energy needed to power FRBs. But here's the problem: repeating bursts don't match magnetar outburst profiles. Their energy signatures are all wrong, like a fingerprint that almost fits but twists in the wrong direction. Some repeaters also emit at frequencies too low for magnetar models, as if something else is tuning the dial. That's where the theories get wild. One proposal suggests cosmic strings, those hypothetical spacetime defects, could be plucking these bursts like guitar strings, each vibration sending a shockwave of radio waves across the universe. Others point to black hole phenomena, like a wandering singularity ripping through a nebula, or a neutron star orbiting a black hole in a deadly dance that periodically sparks radio fireworks. But the most tantalizing idea: these repeaters might be artificial. Not necessarily beacons from aliens, though some scientists won't rule it out, but structures or natural engines so advanced they blur the line between astrophysics and something beyond. Picture a cosmic particle accelerator the size of a solar system, or a Dyson sphere harvesting energy from a star, misfiring in ways that look like FRBs to distant observers. What's undeniable is this: every time a repeater flares, it leaves behind more questions than answers. The universe loves patterns, but these bursts feel less like natural rhythms and more like a cipher, a code we're only beginning to crack. And until we do, these enigmatic signals will keep pulsing in the dark, each one a reminder of how much we still have to learn. Black holes are supposed to be cosmic, one-way doors, places where matter vanishes forever, leaving no trace behind. Yet something impossible is happening in the depths of these gravitational monsters. Somewhere in the swirling chaos just outside their event horizons, black holes appear to be whispering back. Scientists call these signals echoes, mysterious X-ray pulses that arrive milliseconds to seconds after the initial burst, as if the void itself is answering. Take the black hole called XTJ 1550-564. When it flares, X-rays erupt in a predictable pattern, but then, almost like clockwork, faint secondary pulses follow, delayed by precise intervals that shouldn't exist. According to general relativity, nothing escapes a black hole's grasp once it crosses the event horizon. So how are these echoes slipping through? One possibility is that we're witnessing space-time itself twist into knots. As matter spirals toward oblivion, it might create shockwaves that ricochet off the warped geometry near the event horizon, bending light in ways that mimic echoes. Picture shouting into a cave and hearing your voice bounce back, except the cave is a black hole and the walls are made of distorted reality. But there's a wilder explanation. These delays could be evidence of quantum effects at the event horizon, where the rules of relativity and quantum mechanics collide. Some theories suggest black holes aren't perfect traps, that information might leak out via quantum tunneling or holographic projections, creating these eerie afterpulses. It's as if the universe has found a loophole in its own laws, letting faint traces of what's inside slip through the cracks. Then there's the timing puzzle. The delays between initial flares and echoes don't match any known physical process around black holes. They're too consistent to be random noise, yet too irregular to fit cleanly into existing models. Some researchers speculate the echoes might encode the black hole's spin rate or mass, a cosmic fingerprint hidden in the lag between pulses. Others wonder if we're seeing signs of exotic physics, like extra dimensions crumpling near the event horizon, or even remnants of a firewall, a theoretical barrier of energy that could exist at the point of no return. What's truly unsettling is what these echoes imply about the nature of black holes. If they're real, they challenge the very idea that black holes are simple, silent voids. Instead, they might be dynamic, resonant objects ringing like bells in the fabric of space-time. Every pulse could be a clue, a message from the edge of oblivion, hinting at secrets we're only beginning to decode. And until we understand them fully, these ghostly echoes will keep haunting our data, a reminder that even in the darkest corners of the universe, nothing is ever truly silent. Neutrinos are the universe's ultimate ghost particles, so elusive. Trillions pass through your body every second without a single interaction. They're born in the hearts of stars, the fury of supernova, and the violent jets of black holes racing across the cosmos at nearly the speed of light. Yet despite their abundance, catching one is like trying to grab smoke with your bare hands. Most slip through Earth and our detectors without a trace. But occasionally, ultra-high-energy neutrinos strike with such force, they leave undeniable fingerprints in observatories like IceCube, buried deep in Antarctic ice. Here's where the mystery deepens. Some of these high-energy ghosts arrive with no identifiable origin, no nearby supernova, no active galaxy, no pulsar pointed in their direction, just a cosmic blank space where their source should be. It's as if these neutrinos materialized out of nowhere, like cosmic hitchhikers with no starting point. Even stranger, their paths don't align with known gravitational lenses or galaxy clusters that might bend their trajectories. So where are they coming from? One theory suggests these neutrinos might be interacting with dark matter in ways we can't yet detect. Imagine dark matter as an invisible web stretching across the universe. If a neutrino grazes a dense knot of this shadowy substance, it could scatter or redirect, erasing any trace of its original path. It's like a bullet ricocheting off a wall you didn't know was there. The shot came from somewhere, but the bounce points nowhere. Then there's the space-time twist. Could these ghost trails be evidence of hidden warps in the fabric of the universe? Einstein showed us that massive objects bend space-time, but what if there are subtle, invisible curves? Cosmic wrinkles too faint to map with light. Neutrinos barely interacting with matter might be the only particles sensitive enough to trace these contours, revealing bends we've never seen before. The most tantalizing possibility, these neutrinos could be relics of unimaginably distant events, their sources so far away their light hasn't reached us yet. Picture a star collapsing into a black hole 10 billion light-years away. The neutrino blast arrives now, but the light from that cataclysm won't come for another billion years. In that case, these ghost trails aren't missing their origins. We're just too early to see them. What makes these phantom neutrinos so thrilling is their defiance. They refuse to play by the rules, slipping through our best models like shadows through a net. Every time we catch one, it's not just a particle, it's a clue, a whisper from the darkest corners of the cosmos. And until we decode their secrets, they'll keep haunting our detectors, reminding us that some of the universe's greatest stories are written in ink we can't yet see. Between galaxies where darkness should reign supreme, there's a faint glow stitching the cosmos together, threads of gamma rays so vast, they form a sprawling web across the universe. These aren't random streaks of light, they're precise filaments strung between galaxies like cosmic power lines, pulsing with energy that defies easy explanation. What's astonishing isn't just their scale, spanning hundreds of millions of light years, but their eerie symmetry. Natural cosmic processes tend to be messy, chaotic. So why does this web look so meticulously woven? One clue lies in dark matter. If this invisible scaffolding of the universe interacts with itself, colliding or decaying, it could release gamma rays along the densest strands of its hidden architecture. Picture a spiderweb glistening with dew. The gamma rays might be tracing the contours of something far larger, something we've never seen directly. Simulations show dark matter forming similar filamentary structures on galactic scales, but the real-life version glows brighter and more organized than anyone predicted. It's as if we're seeing the shadow of the universe's skeleton, illuminated by high-energy light. Then there's the dimension-hopping hypothesis. Some theories suggest these filaments could be conduits for energy leaking from higher dimensions, like cracks in a wall where light seeps through from the other side. If extra dimensions exist, curled up tighter than an atom, their energy might bleed into our universe along these precise pathways, igniting gamma rays like cosmic fuse wires. It's a wild idea, but the math holds a strange elegance. The filament's spacing and alignment match predictions from certain string theory models, as if the universe left us a breadcrumb trail to deeper physics. But here's the twist: not all filaments connect to known galaxy clusters. Some stretch into voids, threading through emptiness as if tethered to invisible anchors. That's forced scientists to consider even stranger possibilities, like primordial black holes, born in the universe's first seconds, strung along these threads like beads on a necklace. Or perhaps the filaments are cosmic scars, remnants of a phase transition in the early universe when space-time itself rewrote its rules, freezing defects into place that now hum with gamma-ray energy. The most tantalizing detail, the web structure mirrors another cosmic mystery, the distribution of fast radio bursts. Could these high-energy threads be guiding or even generating those enigmatic signals? Or are both phenomena symptoms of something grander, a hidden layer of the universe's operating system, flickering into view just often enough to keep us guessing? Every new observation tightens the knot of this puzzle, weaving together questions about dark matter, gravity, and the very fabric of reality. And until we untangle it, this glowing web will keep hanging in the void, a silent reminder that the universe's grand design is far from decoded. Pulsars are nature's most precise clocks, spinning neutron stars so regular, their pulses rival atomic timekeeping. But every now and then, without warning, one stutters. In a fraction of a second, its rotation speeds up as if someone kicked the cosmic gears. Astronomers call these events glitches, and they're among the strangest hiccups in the universe. Imagine a metronome ticking flawlessly for years, only to suddenly skip a beat, except in this case, the metronome is a city-sized ball of ultra-dense matter spinning hundreds of times per second, and the skip defies everything we know about stellar physics. At first glance, the culprit seems obvious. Neutron stars are born in supernova explosions, their crusts frozen solid under unimaginable pressure. As they spin down over millennia, this crust should crack under stress, causing starquakes that abruptly change their rotation like an ice skater pulling their arms in to spin faster. But here's the catch, the math doesn't always add up. Some glitches release more energy than any quake could generate, while others happen in pulsars too old and cold for crustal shifts. It's as if the universe is handing us a puzzle with half the pieces missing. That's where quantum weirdness enters the picture. Beneath a pulsar's solid crust lies a surreal ocean of superfluid neutrons, swirling with vortices like a hypercharged whirlpool. Normally, these vortices align neatly with the star's spin, but if they suddenly tangle or unpin from the crust, they could transfer a burst of angular momentum to the surface like a spinning top whose hidden core suddenly shifts its weight. The result, a glitch. This theory is elegant, but it raises thorny questions. Why do some pulsars glitch repeatedly while others never do? And why do the intervals between glitches sometimes follow cryptic patterns, as if the star is counting down to its next stumble? Then there's the wild card, magnetic madness. Pulsars boast magnetic fields trillions of times stronger than Earth's, and some models suggest these fields could reconfigure in explosive rearrangements, twisting the star's interior like a cosmic rubber band before snapping it forward. Picture a wound-up toy suddenly releasing all its tension at once, except the toy is a neutron star, and the snap unleashes enough energy to power a supernova. If true, this would mean glitches aren't just hiccups, they're seismic shifts in a pulsar's very soul. What makes these events so thrilling is their defiance. They're not bugs in the cosmic code, they're features, reminding us that even the universe's most precise machines have secrets. Every glitch is a message in a bottle, washed ashore from the depths of extreme physics. And until we crack their cipher, these spinning enigmas will keep stumbling, whispering clues we're only beginning to hear. Cosmic rays usually rain down on Earth in a chaotic jumble, their paths twisted by magnetic fields and chance collisions. So when detectors started catching pairs of particles arriving in perfect mirrored trajectories, it sent shockwaves through the physics community. These aren't just similar particles showing up around the same time. They're cosmic twins, striking from opposite directions with matching energies, as if they'd bounced off some invisible celestial mirror. The odds of this happening randomly are astronomically low, like flipping a coin 1,000 times and getting heads every single time. Whatever's causing this symmetry, it's playing by rules we don't yet understand. One explanation digs into the fabric of spacetime itself. Quantum theory suggests that empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. Could these fleeting particles create temporary hotspots dense enough to scatter incoming cosmic rays, sending them ricocheting back in mirrored pairs? Picture throwing two marbles into a trampoline. If they hit the same wrinkle in the fabric at just the right angle, they'd rebound in perfect sync. The math hints it's possible, but there's a catch. These quantum mirrors would need to be impossibly precise, aligning across vast distances with no room for error. Then there's the multiverse angle. If parallel universes exist stacked like pages in a book, some theories suggest their gravitational pull might warp our space-time in subtle ways. Cosmic rays skimming the boundary between realities could split like light through a prism, with one particle veering into our universe while its twin deflects into another, only to re-emerge moments later from the opposite direction. It's a radical idea, but the mirrored trajectories fit eerily well. The trouble is, we've never detected direct evidence of other universes. If this is their calling card, it's frustratingly cryptic. The most tantalizing clue lies in what these pairs don't show. Unlike typical cosmic rays, which often trail faint electromagnetic whispers, mirrored particles arrive suspiciously clean. No secondary particles, no telltale radiation. It's as if whatever produced them left no fingerprints. Some researchers speculate they're seeing the handiwork of an exotic particle, something that interacts so weakly with ordinary matter. It's effectively invisible except for these mirrored splashes. Others wonder if we're glimpsing a flaw in relativity itself, a hint that spacetime at certain energies behaves less like a smooth fabric and more like a hall of mirrors. What's undeniable is how these mirrored pairs defy categorization. They're not quite natural, not quite artificial, and far too organized to dismiss as noise. Every matched set is a riddle wrapped in cosmic symmetry, challenging us to rethink not just how particles move through space, but what space itself might be hiding. And until we solve it, these reflections will keep arriving, silent and precise, like echoes from a room we didn't know existed. In the vast molecular clouds drifting between stars, where temperatures hover just above absolute zero, something impossible is glowing. Telescopes tuned to the infrared spectrum have picked up faint but persistent bands of light-specific wavelengths that don't match any known molecule in our databases. Dubbed the unidentified infrared bands, these signals have haunted astronomers for decades, appearing in nearly every corner of the galaxy where interstellar dust gathers. It's as if the cosmos is broadcasting a chemical fingerprint, but we're missing the key to decode it. At first, scientists assumed these bands were just the signatures of simple carbon-based molecules, like polycyclic aromatic hydrocarbons, the soot-like compounds found in candle flames and car exhaust. But the more they studied them, the clearer it became. These infrared signatures are too complex, too structured, to belong to ordinary space dust. The patterns resemble the vibrational frequencies of large organic molecules, hinting at compounds far more intricate than anything we've synthesized in labs. Some researchers speculate they could be prebiotic molecules, the building blocks of life floating in the void, forged in the cold nurseries of star-forming regions. Imagine stumbling upon a cosmic recipe book, its pages filled with formulas we've never seen before. Yet there's a twist. These bands don't behave like typical organic material. They're eerily resilient, surviving environments where radiation and cosmic rays should tear them apart. In the harsh outskirts of planetary nebulae or the violent shocks of supernova remnants, where even hardy molecules like Buckminster fullerene break down, the unidentified infrared bands persist, glowing like unshakable ghosts. This durability suggests they're not just random assortments of atoms, but something more organized, perhaps molecular networks with a stability that defies conventional chemistry. That's where the theories get wild. One hypothesis points to exotic carbon structures like graphene-like sheets or carbon nanotubes woven into interstellar dust. Another proposes that these bands could be the traces of quantum dots, nanoscale crystals that emit light at specific frequencies when energized, but the most tantalizing idea. They might be evidence of entirely new forms of matter, with bonding configurations or quantum properties we haven't yet discovered. Picture a chemistry textbook where whole chapters are missing, waiting to be written by these enigmatic signals. Astrobiologists are particularly fascinated. If these bands do trace complex organics, they could be the universe's way of seeding life's ingredients across galaxies. But here's the puzzle. Why haven't we recreated these signatures in labs? Despite decades of effort, no experiment on Earth has perfectly replicated the unidentified infrared bands. It's as if space holds a secret recipe, written in conditions so alien our technology can't yet mimic them. The deeper we look, the more questions arise. Some of these bands appear stronger in regions where stars are forming, while others dominate the diffuse clouds between stars. Are they byproducts of stellar birth, or do they form in the quiet darkness of deep space? And why do certain wavelengths appear together like a cosmic barcode in ways that suggest an underlying order? What's certain is this: these infrared whispers are more than just cosmic static. They're a challenge, a reminder that even in the coldest, emptiest reaches of space, the universe is still cooking up mysteries we can't yet taste. And until we crack their code, these bands will keep glowing in the dark, silent and stubborn, like a riddle etched in light. Gamma-ray bursts are supposed to be the universe's most violent farewells, cosmic fireworks that flare brightly before fading into lingering afterglows. But some break the rules entirely. These bursts erupt with staggering energy, then vanish into the dark without a trace, like a firework that explodes midair and leaves no smoke, no sparkle, nothing. Scientists call them naked gamma-ray bursts, and their abrupt endings hint at something far stranger than a typical stellar collapse. When a massive star dies, it usually leaves behind either a neutron star or a black hole, both of which produce detectable afterglows as surrounding matter crashes into them. But these empty bursts suggest a third possibility. The star might be collapsing into something even more exotic, like a quark star. Picture a neutron star squeezed beyond its limits, its protons and neutrons dissolving into a soup of free floating quarks. Such an object would be so dense it could swallow energy whole, leaving no afterglow behind. It's like dropping a stone into a bottomless well. You hear the splash, but the ripples never come. Then there's the black hole scenario, but not the kind we're used to. Normally, black holes announce their presence with bright accretion disks, swirling with superheated gas. But what if one formed without any debris to feed on? A star collapsing directly into a black hole in near-empty space would have nothing to glow, vanishing like a shadow in a darkened room. The energy from the burst would simply disappear, swallowed by the void. The real puzzle is where all that energy goes. Gamma-ray bursts release more power in seconds than our sun will in its entire lifetime. For that energy to vanish without a trace defies everything we know about conservation laws. Some theorists speculate it might be funneled into gravitational waves or even hidden dimensions, leaking out of our universe entirely. Others wonder if we're seeing the birth of something entirely new, a state of matter so unstable, it flickers out of existence almost as soon as it forms. What makes these empty bursts so unsettling is their silence. Most cosmic events leave echoes, radiation, shockwaves, something. But these are cosmic dead ends offering no clues, no trails to follow. Every time one flashes and fades, it's like the universe is teasing us with a riddle it refuses to solve. And until we catch one in the act, with instruments precise enough to spot what happens in those final milliseconds, these ghostly bursts will keep challenging our understanding of how stars die and what they leave behind in the dark. Zoom in far enough, past galaxies, past stars, past even atoms, and reality itself might start to look foamy. Quantum mechanics tells us that at the tiniest scales, space-time isn't smooth and polished like glass, but churning and chaotic, a seething ocean of virtual particles blinking in and out of existence. This so-called quantum foam should leave fingerprints in cosmic radiation, subtle fluctuations where the fabric of reality flickers like static on an old TV. And here's the kicker, we've found them. Radiation detectors have picked up faint, erratic pulses that look exactly like spacetime's granularity, except for one glaring problem. The patterns don't match any existing quantum gravity theory. They're too loud in some frequencies, too quiet in others, as if the universe is playing a game where we only know half the rules. Take loop quantum gravity, for example. This framework predicts spacetime should break into tiny, discrete loops at the Planck scale. Think of pixels on a cosmic monitor. The radiation fluctuations from these loops should follow a very specific mathematical rhythm, a signature we've hunted for decades, but the signals we're catching, they're more like a jazz improvisation, full of irregular beats and off-key notes. String theory doesn't fare much better. Its higher dimensional vibrations should produce a subtler, more harmonic noise, yet the data shows spikes and dips in all the wrong places. It's like tuning a radio and hearing music, but the melody belongs to a song no one's ever written. Then there's the timing mystery. Some fluctuations appear to cluster in ways that suggest spacetime isn't just foamy. It might be lumpy, with dense knots of quantum activity separated by eerily quiet voids. Picture the foam on a cappuccino, where some bubbles clump together while others leave wide gaps. Except in this case, the bubbles could be flaws in reality itself, regions where the universe's underlying code glitches for fractions of a second. The wildest part, these anomalies aren't rare. They're everywhere, woven into the cosmic background like static in an old film reel. If this truly is quantum foam, it's far more turbulent than anyone predicted. Some researchers argue we might be seeing evidence of spacetime's memory, residual energy from the Big Bang still vibrating in the fabric of the cosmos. Others wonder if we're glimpsing the edges of something bigger, like a cosmic hologram where our 3D reality is just a projection of deeper, more fundamental processes. What's clear is this: the universe isn't just hiding its secrets in black holes or distant galaxies. They're right here, etched into the tiniest flickers of radiation, waiting for us to decode them. And every mismatch, every unexplained blip, is a reminder that the deepest mysteries aren't always written in the stars. Sometimes they're hiding in the noise. Dark matter is supposed to be the universe's silent scaffold, an invisible, evenly distributed glue holding galaxies together. But something's off. Instead of forming the smooth, diffuse halo we've come to expect, it's clumping together in dense, unpredictable knots, warping the paths of cosmic rays like stones in a riverbed. These aren't just minor wrinkles in the data, they're glaring contradictions forcing scientists to ask, is dark matter playing by rules we don't understand? or are we missing something fundamental about gravity itself? Picture tossing a handful of marbles onto a trampoline. You'd expect them to roll smoothly toward the center, creating a gentle dip. But what if some marbles inexplicably clustered in tight groups, creating deep, isolated pits in the fabric? That's essentially what's happening with dark matter. Simulations based on our current models, like the celebrated lambda-cold dark matter framework, predict a universe where dark matter flows in broad, even waves. Yet when astronomers map its distribution using gravitational lensing or cosmic ray distortions, they find bizarre hotspots, regions where dark matter piles up like snowdrifts in a windstorm. One of the most striking examples lies in the dwarf galaxy Segway 1. This tiny satellite of the Milky Way should be drowning in a smooth sea of dark matter, but observations reveal it's actually sitting at the heart of a dense, compact clump, far more concentrated than any simulation anticipated. It's as if dark matter there decided to ignore the rulebook entirely. Similar anomalies pop up in galaxy clusters like El Gordo, where gravitational lensing suggests dark matter isn't just clumping, it's segregating itself from ordinary matter in ways that defy every expectation. Theories scramble to explain this. Maybe dark matter isn't entirely cold as we've assumed. If these particles have even a tiny bit of thermal motion, what physicists call warm dark matter, they could resist smoothing out, leaving behind clumps like flour that wasn't fully sifted. Others propose dark matter might interact with itself through some unknown force, creating friction that causes it to pile up in certain regions. Imagine pouring sand onto a sheet of ice. If the grains stick to each other but slide effortlessly over the ice, they'd form uneven mounds rather than spreading evenly. But the most radical idea, gravity might not work the way we think it does. Modified Newtonian dynamics, or MUND, suggests that on cosmic scales, gravity's strength doesn't follow Einstein's rules, meaning dark matter's apparent clumps could be illusions, shadows cast by a flaw in our fundamental physics. It's a controversial take, but the persistence of these anomalies keeps the door open. What's truly mind-bending is how these clumps warp cosmic rays. Particles streaking through space should bend gently around large dark matter structures like light through a lens. Instead, some rays zigzag sharply, as if they're hitting invisible speed bumps. If dark matter's distribution is as lumpy as the data suggests, it would mean the universe's hidden skeleton is far knottier and far stranger than we ever imagined. Every clump we find is a breadcrumb leading us deeper into the dark. Whether they're proof of exotic physics, gravitational rebellion, or something entirely unseen, one thing is clear: the universe's quietest ingredient is shouting at us to look closer. And until we decipher its message, these dense, defiant knots will keep challenging everything we thought we knew about the cosmos's hidden architecture. Beneath the cacophony of exploding stars and colliding galaxies, the cosmos is humming. Not in the metaphorical sense. This is a literal, measurable vibration rippling through space-time itself, a low-frequency drone so pervasive it blankets the universe like sonic wallpaper. Gravitational wave observatories first caught whispers of it, not the sharp chirps of black hole mergers or the crescendos of neutron star collisions, but something far subtler, a background hum, steady as a tuning fork struck at the dawn of time. The strangest part, this hum doesn't match any known cosmic rhythm. It's too constant to be the work of random black hole mergers, too uniform to be the echo of primordial supernova. One leading theory points to supermassive black holes, not the dramatic collisions we've come to expect, but slow, stately dances as these behemoths spiral toward one another over millions of years. Picture two whales circling in the deep, their gravitational ripples blending into a sustained tone. The math almost fits, except the hum's volume is louder than it should be, as if the universe is hiding more of these orbiting giants than our telescopes can see. Then there's the cosmic string hypothesis. These theoretical filaments, infinitely thin cracks in space-time left over from the universe's birth, could vibrate like guitar strings, ringing out gravitational waves as they snap or loop. The hum's frequency aligns eerily with predictions for how these strings might sound, a cosmic bass note thrumming across eternity. But here's the catch: we've never definitively detected cosmic strings. If they're the source, this hum would be their first tangible signature, a ghostly fingerprint from the universe's first moments. Yet the most tantalizing possibility lies in the hum's timing. It's not just present, it's persistent, unchanged across billions of years of cosmic evolution. That consistency hints at something deeper than astrophysical events, a fundamental vibration woven into space-time itself, like the resonant frequency of a bell forged in the Big Bang. Some models even suggest this hum could be the collective heartbeat of dark matter, its particles oscillating in unison on scales too vast to comprehend. What's undeniable is how this hum defies silence. The universe isn't just alive with light and motion, it's singing, in a voice too low for ears but unmistakable to science. Every time we listen, we're hearing more than noise. We're hearing the cosmos whisper its oldest secrets in a language we're only beginning to decode. Cosmic rays usually scatter like buckshot, their paths twisted and randomized by the chaos of interstellar space. So when detectors started catching them in braided clusters, twisted together like strands of a rope, physicists knew something extraordinary was happening. These aren't just random particles arriving at the same time. They're entangled in structure, their energies and trajectories coiled around one another with uncanny precision. It's as if the universe tied these particles into knots before hurling them across the void. What makes these cosmic ropes so baffling is their defiance of magnetism. Galactic magnetic fields are strong enough to bend individual cosmic rays into wild arcs, yet these bundles stay locked together, their cohesion unbroken even after journeying millions of light years. Imagine throwing a handful of needles into a tornado and watching them land perfectly threaded into a straight line. That's the level of improbability we're dealing with. One explanation points to dark energy, the mysterious force accelerating the universe's expansion. If dark energy interacts with matter in ways we don't yet understand, it might weave particles into these dense, stable braids, like invisible hands plaiting cosmic threads. Then there's the primordial possibility. These ropes could be relics from the universe's first seconds, when space-time itself was a seething plasma of quantum turbulence. In that chaos, topological defects, kinks, or twists in the fabric of reality might have trapped particles in their grip, preserving these twisted configurations like bugs in amber. Picture the early cosmos as a pot of boiling water, with bubbles and vortices forming spontaneously. If some of those vortices froze into place as the universe cooled, they could have carried these particle ropes across billions of years, untouched by time. The real enigma lies in the rope's structure. They're not just clumps, their particles are arranged in helical patterns, as if spun by some cosmic spindle. This level of organization is unheard of in high-energy physics, where randomness usually reigns. Some theorists speculate they're seeing the fingerprints of an unknown force, one that operates only at energies so extreme they're unreachable in our particle colliders. Others wonder if these ropes are signatures of higher dimensional physics, evidence that our 3D universe is brushing against hidden geometries, where particles can tangle in ways that seem impossible here. Detecting them is like trying to catch smoke with bare hands. Most observatories aren't designed to spot correlated particle bundles, so these ropes often slip through unnoticed. But when they do appear, they leave a glaring question mark in the data. Why do some ropes contain particles with identical energies, while others mix wildly different ones? And why do a few seem to unravel mid-flight, their strands dispersing as if some invisible binding force suddenly snapped? The implications ripple far beyond curiosity. If these ropes are dark energy's handiwork, they could be the key to understanding why the universe is tearing itself apart. If they're primordial, they're time capsules from the Big Bang's first moments. Either way, they're proof that even the simplest particles, when woven into the cosmos's hidden patterns, can carry secrets that rewrite the rules. And until we untangle them, these braided mysteries will keep sailing through space, silent and tight-knit, daring us to pull the right thread. Dark energy was supposed to be the universe's great constant, an unchanging force stretching space-time apart at a steady, predictable rate. But the cosmos has a habit of defying expectations. Recent observations reveal something unsettling. Dark energy's strength isn't uniform at all. In some regions of space, it's as if the universe is pressing harder on the accelerator, while in others, it's barely touching the pedal. These fluctuations aren't just statistical noise. They're deviations so stark, they've forced cosmologists to confront a radical possibility. Dark energy might not be one thing, but many. Take the Hubble tension, a nagging discrepancy in how fast the universe is expanding. Depending on where and how we measure, the numbers refuse to align. Some galaxies recede as if dark energy's push has intensified, while others drift apart at the expected pace. It's like watching cars on a highway where some inexplicably speed up while others cruise steadily, with no traffic patterns to explain the difference. If dark energy were truly uniform, this shouldn't happen. One explanation: dark energy might be evolving. Imagine a river that starts as a gentle stream but grows into a raging torrent downstream. Similarly, dark energy could have been weaker in the universe's youth, gaining strength as space-time stretched. This idea, called quintessence, suggests dark energy isn't a static force but a dynamic field, ebbing and flowing across cosmic time. The problem is, our models can't yet pin down how or why it would change. Then there's the multiverse angle. If our universe is just one bubble in a froth of others, each might have its own flavor of dark energy with slightly different strength. Where these bubbles brush against one another, dark energy could appear to flicker like streetlights dimming at the edge of two power grids. It's a wild idea, but the math holds a haunting elegance. The most unsettling possibility: we might be seeing the fingerprints of an entirely new physics. Dark energy's patchiness could hint at undiscovered particles or forces that interact with it, sculpting its influence like invisible hands kneading dough. Or worse, what if dark energy isn't a force at all, but a shadow, a side effect of some deeper, hidden process we've yet to uncover? Every inconsistency is a crack in cosmology's foundation. If dark energy isn't constant, our entire understanding of the universe's fate, whether it will rip apart, freeze over, or collapse, is up for grabs. The phantom isn't just hiding in the data. It's rewriting the rules, one mysterious fluctuation at a time. Every so often, the universe lobs a fastball at Earth so powerful, it shatters every rule in the physics playbook. These are the oh my god particles, cosmic rays packing energies 100 million times beyond what the Large Hadron Collider can produce. To put that in perspective, a single one of these particles carries the kinetic energy of a baseball hurtling at 60 miles per hour but compressed into a subatomic speck. They shouldn't exist. According to relativity, particles accelerated to such extremes should lose energy as they collide with the cosmic microwave background. the faint afterglow of the Big Bang. Yet here they are, slamming into our detectors with no regard for theoretical limits. The mystery deepens when we trace their origins, or try to. These particles don't point back to any known cosmic powerhouse. Supermassive black holes colliding galaxies, even gamma-ray bursts, none of them seem capable of firing such extreme projectiles across the universe without the energy bleeding away. It's like finding a bullet that traveled halfway around the world without slowing down. One theory suggests these particles might be riding cosmic shortcuts, wormholes or wrinkles in spacetime that let them bypass the usual energy-sapping obstacles. Picture a highway with hidden tunnels. These particles could be slipping through unseen passages, arriving with their energy intact. Then there's the dimensional wildcard. If higher dimensions exist beyond our four familiar ones, as string theory proposes, particles from those realms might occasionally leak into our universe, bringing energies calibrated to a different set of physical laws. Imagine a wave crashing onto a two-dimensional shore. To flatlanders, it would seem like an impossible surge of energy appearing from nowhere. Could oh my god particles be similar dimensional refugees, their true origins as alien to us as oceans are to paper-thin beings? But the most unsettling possibility is that these particles are cosmic breadcrumbs, leading us toward flaws in our understanding of physics itself. The GZK limit, a theoretical boundary named for the scientists who calculated it, predicts a hard ceiling for cosmic ray energies based on how they interact with the cosmic microwave background. Oh my god, particles blow past that limit like it doesn't exist. Either our models of particle interactions are missing a critical piece, or the universe has a way of accelerating matter that defies every equation we've written. What's clear is this: these particles aren't just outliers, they're cosmic stress tests probing the edges of our knowledge and finding them far more flexible than we imagined. Every time one streaks through a detector, it's not just a particle, it's a question written in the universe's boldest handwriting. And until we crack its code, these impossible messengers will keep arriving, silent and staggering, daring us to rethink the rules of reality. When faced with cosmic anomalies that defy every textbook, scientists don't just shrug, they rewrite the rules. Take modified gravity, for instance. Einstein's theory of general relativity has been the bedrock of cosmology for over a century. But what if it's incomplete? Some researchers argue that these 27 patterns could be cosmic breadcrumbs, leading us toward a new understanding of gravity itself. Imagine gravity isn't a constant force but behaves differently at galactic scales, warping space-time in ways we've never accounted for. This isn't just tweaking equations, it's questioning the very fabric of how we perceive the universe's structure. Then there's the multiverse hypothesis. If our cosmos is just one bubble in an infinite foam of universes, collisions between these bubbles could leave scars, imprints in cosmic radiation, or bizarre particle behaviors that seem inexplicable from our limited vantage point. Picture two soap bubbles merging in a sink. The ripple where they touch would look like pure chaos to a microbe living on one surface. Could these 27 anomalies be our glimpse into that collision zone, where the laws of physics blur at the edges? Of course, not all theories are so cosmic in scale. Some focus on the unseen particles lurking in the shadows. Actions, for example, hypothetical particles born from quantum field theory, could explain certain radiation patterns if they're out there, drifting like invisible fog through space. Other models propose sterile neutrinos, ghostly cousins to the neutrinos we know, which might interact only via gravity, leaving faint but detectable traces in cosmic ray data. These aren't just placeholder ideas, they're testable predictions with experiments like the upcoming LUX Zeppelin detector hunting for their signatures right now. And yes, a handful of researchers dare to whisper about extraterrestrial origins. Not little green men, but advanced civilizations harnessing energies we can't yet fathom. Imagine a Kardashev-type Roman II civilization building megastructures around stars, their waste heat manifesting as anomalous radiation patterns. It's a fringe idea, but even skeptics admit it's a useful thought experiment pushing us to ask, how would we know if we weren't alone? The answer often circles back to Occam's razor. The simplest explanation is usually right. Yet when the simplest explanation keeps failing, the door cracks open for wilder possibilities. What unites all these theories isn't just creativity, it's humility. Each anomaly is a mirror reflecting how much we still don't understand. Whether the answer lies in tweaked equations, hidden dimensions, or particles we've yet to name, one truth remains: the universe is playing a game with rules we're only beginning to decode. And every time we think we've got it figured out, the cosmos throws another curveball, reminding us that the greatest discoveries often start with the words, "Huh." That shouldn't happen. These 27 cosmic riddles aren't just scientific curiosities, they're glaring signposts in the dark, marking where our maps of reality end and the uncharted begins. Think of each anomaly as a crack in the foundation of modern physics, with revelations spilling through like light through a broken dam. The galactic center's gamma-ray symmetry, the eerie precision of those gamma-ray circles, even the way cosmic rays braid themselves into ropes, they all whisper the same unsettling truth. We're still cosmic toddlers, barely scratching the surface of what's out there. What makes these mysteries so electrifying isn't just their existence, but how they intertwine. That strange lithium shortage in the early universe, it might connect to the same quantum foam fluctuations that twist space-time at microscopic scales. The dark flow dragging galaxy clusters toward the void could be tugging on the same cosmic strings that leave gamma-ray loops across the sky. Even the hum of gravitational waves might be harmonizing with the vibrations of those unseen dimensions where oh my god particles slip through. Every anomaly is a thread in a web we're only beginning to trace, each one pulling us deeper into the labyrinth. This isn't about filling textbooks, it's about rewriting them. When the Fermi Bubbles' razor-sharp edges defy fluid dynamics, or when the cold spot stares back at us like a bruise from a multiverse collision, we're not just adding footnotes to science. We're witnessing the birth of new physics where dark matter might not be matter at all, where gravity could be an emergent illusion, and where the fabric of space-time itself might pixelate into quantum code if we zoom in close enough. The real magic lies in the questions we haven't even thought to ask yet. So here's the invitation: keep watching the stars, but also the spaces between them. That faint glitch in a telescope's data, that blip in a particle detector, they might be the first murmurs of the next revolution. Because history shows us the greatest leaps begin where the equations break down. Whether you're a backyard stargazer or a physicist running simulations, remember, every cosmic that's impossible is just a frontier waiting to be crossed. The universe hasn't run out of surprises. It's just waiting for us to catch up. End screen animation appears with pulsar sounds, fading to black with a final gamma ray burst visual effect.